All right, in this lesson, we're going to talk about key features of exponential functions. So an exponential function is any function of the form f of x equals a times b to the x, where a and b are constants, with a not equaling 0 and b being greater than 0, and also b can't be 1. So when your b value is greater than 1, that is going to represent a growth. And when your b value is between 0 and 1, that is going to represent a decay. All right. So what are the key features of each function? We're going to include the domain, range, intercepts, asymptotes, and our end behavior. So if you're looking at this equation, 2 to the x, we have no restrictions on the domain because x can be any number, all right, any integer. So well, not just integer, just any real number. So we have no restrictions on our domain. So for the domain, it's negative infinity to positive infinity, so just all real numbers. Now, if you're a visual person, you could graph this. So let's graph it and take a look at it. So 2 to the x. All right, as you can see, it is a growth. It rises from left to right, okay? So you can see this continues to the left, it continues to the right, so I have no restrictions on my x values. So for my range, though, I can see right here, there is an asymptote there. Anytime you see this kind of getting really close to something, but it doesn't go anywhere, it's just kind of flattening out, you have an asymptote there. And if you go to your table, the more x gets negative, the closer these y values are getting to 0, okay? So my range would be 0 and bigger, but we can't include 0. So for my range, we're going to put a parenthesis to show that we don't include 0, just everything right next to 0, and then to infinity. So your y values need to be greater than 0. So let's talk about your y-intercept. Now every y-intercept has an x value of 0. Now I can visually see my x-intercept right there at 1, but if you look at the table, right there, when x is 0, y is 1. So my y-intercept is at 1. All right. Now, we already talked about the asymptote. The asymptote is right there at y equals 0, or the x-axis. All right, and then end behavior, which we have discussed before, just talks about what happens at the ends of your equations. So let's talk end behavior. So as x approaches negative infinity, y is going to approach something. And as x approaches positive infinity, y is going to approach something. So remember, this part of your statement is always the same. And the only thing that changes is where your y is headed. So your x's are either heading towards negative infinity or towards positive infinity, and then you state what your y is doing. So let's take a look at that. So if you look, as my x's are getting more and more negative, my y values are getting closer and closer and closer to 0. That's because I have an asymptote right there. So as x approaches negative infinity, y approaches 0. On the right side, as my x's get bigger and bigger, my y values are also getting bigger and bigger and bigger. So it is approaching positive infinity. So left side, we're approaching 0. Y side, we're approaching positive infinity. All right, so let's take a look at number 2. Again, domain, still all real numbers. All right, range, still going to be 0 to infinity, or y is greater than 0. But let's go ahead and graph it and take a look at it. So we have 5 times 1/2 to the x. All right, now this is a decay function. I'm going down from left to right. I can see that my asymptote is still there at y equals 0. This time, though, my intercept has changed, And now when x is 0, y is 5. I can also visually see it right there. All right, so y-intercept is at 5. Now you might be noticing that there is a part of your equation that can tell you where your y-intercept is. All right, and that would be this number that's in front of the base with the exponent. All right, so my y-intercept is at 5. So on this one, the base was 2, so there would be a 1 in front of that. So 1 was my y-intercept. Now, the second that I maybe add like 4 back here, that's going to shift my entire graph up. So if my y-intercept was at 5 and I shift it up 4, now my y-intercept is at 9. So you have to pay attention to that. If you add or subtract a number back here, you're going to have to add or subtract that number to your y-intercept as well. Okay. So our asymptote we already decided was still at 0. And that's another thing. If your asymptote is at 0, but you add 4 to your entire equation, everything shifts up 4. So if your asymptote was at y equals 0 and I add 4 to that, now my asymptote is at y equals 4. All right? So let's talk the end behavior. So as x approaches negative infinity, y approaches something. And as x approaches positive infinity, y approaches something. So left side, right side. Take a look. On the left side, as our x's are getting more and more negative, our y values are getting more and more positive. As our x values are getting more and more positive, our y's are getting closer and closer to 0. So left side, we're approaching positive infinity. Right side, we're approaching 0. Now that's another thing. If I shift that asymptote up 4, what my x is approaching is also going to shift up 4, so this would then be 4. So because this was a 2 on number 1, because this was a 2, that makes a growth because it's bigger than 1. Because this is 1/2, the base of that exponent is 1/2, that makes a decay because it's between 0 and 1. So number 3 is going to be a decay as well. All right, so let's talk domain and range. So for the domain, we are still negative infinity to positive infinity, all real numbers. Range, we did not shift this up at all, so we are still 0 to infinity, or y has to be greater than 0. All right, y-intercept, I'm going to look at that number that's in the front. My y-intercept is 4. My asymptote is still at 0 because I didn't shift this up, so y equals 0. And for my end behavior, as x approaches negative infinity, y approaches something. And as x approaches positive infinity, y approaches something. Now, since this is a decay, it's going to go down from left to right. So on the left side, my y's are getting more positive. On the right side, they're getting closer to 0. All right, we're going to graph each function. Describe the graph in terms of transformations from the parent function. We're using 3 to the x. How do the asymptote and intercept of the given function compare to the asymptote and intercept of the parent function? So the only thing that changed from this equation to what we have now is we multiplied by a negative. Now this is a growth equation because 3 is larger than 1. So I know that we go up from left to right, which means it's going to flip it downward like this because we multiplied by a negative. All right. So let's go ahead and get a table of values. And I'm going to graph both of these at the same time. So I'm going to put the negative 3 to the x in the first equation and 3 to the x in the second. So the first one will be after we made the change of multiplying by the negative. The second one that's graphing in red is going to be our original parent function. All right, so we can see that's exactly what happened. It just mirrored or reflected over the x-axis. So a reflection over x-axis. All right. It also wants us to compare the asymptote and the intercept. So if you take a look at that, my asymptote on my original, which is the red one, was at 0. And here at the blue, it's still at 0. Nothing has changed. It's just flipped upside down. My intercept was at 1, and because we mirrored that over the x-axis, it's now at -1. All right, so the asymptote is the same. But our y-intercept changed from 1 to -1. Now let's get that table of values and graph. Now if I'm in my table here, this is reasonably the probably closest point to that asymptote I'm going to get. So I'm going to graph here, and I'm going to graph all the way down to 2, -9. Once I get to 3, -27, I can't fit that on my graph, so I'm not graphing that point. So I'm going to make a table of values out of these. So I have -1, -0.3, 0, -1, 1, -3, and 2, -9. And we are just going to graph those points over here. So -1, -0.3, 0, -1, 1, -3, and 2, -9. Now remember, you do have an asymptote here at 0. So when you come up here, make sure you don't cross that. And put arrows on the ends. All right, number 5. So the only thing that changed is we subtracted 4, which means this takes our graph, the original one, and shifts it down 4. So we're going to say we went down 4. That's what the transformation would be. All right, now normally our asymptote is going to be at 0. However, since we moved down 4, our asymptote is now at 4. So our asymptote is at -4. All right. Also, our intercept is at 1. Remember, it's that number that's going to be in front of the base to the exponent. So it's at 1, but we moved it down 4. So we take 1, subtract 4. That gives us -3. So the y-intercept changed from 1 to -3. Now we're going to go ahead and graph this, and you'll be able to see visually what we're talking about. So clear out that original number 4 one. Now again, this was what we started out with, so I'm going to leave that one there. This one is the new one. So you can visually see our y-intercept was at 1, now it's at -3. Our asymptote was at 0, now it's at -4, and it just shifted down 4 units. All right, so get your table of values. Now I do want to point this out. We can see that these y values are getting closer and closer to -4. Eventually your calculator just rounds it. So we don't ever actually reach -4, but your calculator is rounding that. So I'm going to start with the -1, -3.7, and graph all the way to the 2, 5. So I have -1, -3.7, 0, -3, 1, -1, and 2, 5. 1, 2, 3, 7, -3, -1, +5. Now remember, you have an asymptote there at -4, so make sure you don't cross that there. All right, so number 6 and number 7 are exactly the same. The only difference is we're not graphing them. Okay, so we're going to talk about the asymptote and the intercept. So I started with 5 to the x, but I've added a 3 up here. Okay, now you can graph them and look at them if you want to. I already know that if I added that 3 back here, that would mean that I went up 3. So if we think back to when we did transformations, if I add or subtract a number to my x value, like I am here, that moves it left or right, and it's always the opposite. So if you think +3 means right, it really means left. So this is left 3. All right, our asymptote did not change, so asymptote is the same. However, the y-intercept is going to change since we shifted this to the left. So grab your calculator, and we're going to put these in. So I've got 5 to the x plus 3, and then 5 to the x as our original. So you can see, here's our original in red. We shifted to the left. So my intercept was at 1. Now, if you look at your blue graph, when x is 0, y is 125. So we went from 1 to 125. So y-intercept changed from 1 to 125. All right, so number 7. We're multiplying a negative times this x up here. So if you have a reflection over the x-axis when you put the negative out front, then you would have a reflection in the y-axis. So we have a reflection over y-axis. Because I'm adding 6 back here, that means we're going to move up 6. So our asymptote will change from 0 to 6 because I'm adding 6 and moving my graph up. The y-intercept is also going to change. So our y-intercept started at 1. We went up 6. So the y-intercept changed from 1 to 7 because 1 plus 6 is 7. All right, the population of a large city was about 4.6 million in the year 2020 and grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over that 4-year period? So let's think about this. In year 1, my population is, or not 0 years from 2020, my population is 4.6. So if I want to figure out the population for the next year, I have to take my original 4.6 and add a growth of 1.3%. Now, when we multiply a percent, we do it as a decimal. So I'm going to change 1.3 to a decimal. That would be 0.013. And I'm going to take that times the 4.6. So 4.6 times 0.013 gives me how much it grew. Now, I need to make this a little nicer to look at. So I'm going to think of this as being 4.6 times 1. And I'm going to think, what does this term and this term have in common? 4.6. So if I factor a 4.6 out, that leaves me with 1 plus 0.013, which is 4.6 times 1.013. All right. So that's my growth and how much population I would have in this next year. So for the second year, I would take how much I had in the first year. All right. And then I'm going to have to, again, think about the next growth. So I'm going to multiply it times the 1.013. That gives me 4.6 times 1.013 to the second power. So in the third year, it's going to be 4.6 times 1.013 to the third power, so on and so forth. So we have to the first power, to the second power, to the third power. So our equation would be y equals 4.6 times 1.013 to the x, because that would be the number of years since 2020. So part B says, if the population continues to grow at the same rate, what will the population be in 2050? Well, 2050 is 30 years from 2020. So I'm going to plug 30 in for x, because x represents years since 2020. And that's going to give us 6.78. I'm going to round that. And then our unit of measure is millions. So 6.78 million people. All right, number 9, a factory purchased a 3D printer in 2022 for $35,750. The value of the printer depreciates, that means the value goes down, every year by 22%, meaning that it retains 78% of its purchase price for the year, each year that passes. We're supposed to write a function that represents the value of the printer in terms of X, the number of years since 2022. Now, if you look at the equation that we did on number 8, all right, this is the initial amount that you have. That was our initial population. This represents our growth. Now, I know it's a growth because it's above 1, right? Well, you need to be thinking how much above 1, because that would represent 1 plus 0.013. I am 0.013 above 1, so that's why I added it together. That is a growth. When you have a decay, you're not adding to 1, you are subtracting from 1. So if I know that I'm going down 22%, if I make that a decimal, that'd be 0.22. I would be taking away 0.22, which would leave me with 0.78. They gave you that. So this represents my decay rate. So I have y equals initial amount is 35,750 times my rate of decay, which would be the 0.78. Again, I'm less than 1 because I'm thinking it's 22% less. All right, 22% less. So 0.22 less than 1. And then I raise that to the x power for number of years since 2022. What is the value of the printer after 3 years? Well, I'm going to take that equation and I'm going to plug in 3. Now it says to the nearest dollar. So when we plug that in, that would be 16,965. So now after 3 years, it's only worth 16,965. That's a pretty big loss of value. All right. Does the printer lose more of its value in the first 3 years or in the second 3 years? Well, let's see how much value it lost in the first 3 years. So I take my original value, subtract the value at 3 years, which is 16,965. That gives me a loss of $18,785. All right, so in the first after 3 years, it's lost $18,785 worth of its original value. Now, I need to know about the second 3 years. So if I have my first 3 years, I go 3 more years. That's 6 years. So we need to know what is the value after 6 years. So I'm going to take my equation and I'm going to plug in 6. That's going to give us $8,050.89, so $8,051. So it is worth $8,051 after 6 years. They want to know, though, did it lose more value the first 3 years or the second 3 years? So I just need to know about that 3-year period between 3 years and 6 years. So at the end of the third year, the value was $18,785. At the end of 6 years, it's $8,051. If I subtract those, that's $8,914. So it only lost $8,914 of its value in that 3-year period, the second 3 years. So we definitely lost more the first 3 years. So the first 3 years are when we lost the most. All right, so this concept with exponential growth and decay is literally what we just came up with, all right? So we know that inside here, the base is 1 plus our rate. That's a growth, all right? And then 1 minus, that would be our decay, okay? So let's look at number 10. The function y equals 24 times point A to the x can be used to model the value of a car in thousands of dollars X years after it was purchased. Now, does this function represent growth or decay? Well, if I look at the base of that exponent, it's less than 1, so this is definitely decay. All right, what is the rate of decay? Well, think about how much lower are you than 1? Okay, so 1 minus something equals 0.8. Now, I feel like this one is easier. And really, honestly, all you have to do is say 1 minus 0.8. That gives you 0.2. So we have 20%, because I would change that to a percent by moving the decimal 2 places. So we have a 20% rate of decay. I'm keeping 80%. Okay. What does it mean? Well, we're talking about the value of a car. So the value of the car decreases by 20% each year. So each year, my car's value is decreasing 20% from the previous year. All right, what do the y-intercept and asymptote represent, and when will the value of the car be about 5,000? So let's use our calculator to kind of assist us in this. Make sure you take out anything that you might have in there. So we have 24 times 0.8 to the x. All right, so let's talk about the y-intercept first. All right, the y-intercept here is 24. Now remember, x represents years after it was purchased. So 0 years have passed since I purchased my car. The value of the car is represented by the y value. So this is in thousands. So when I bought the car, because no time has passed, it is worth 24,000. So that is my purchase price of the car. So the y-intercept is $24,000, which is the purchase price of the car. All right, let's talk about the asymptote. So my asymptote is going to be at 0 because I didn't shift this up or down. So my asymptote is at 0. Remember, y equals 0. So this just means that the price of my car is going down and getting closer and closer to a value of 0. All right, so for the asymptote, the value of the car is approaching 0. All right, and when, that's an x value, will the value of the car be 5,000? So I'm looking for an x value when the y value is 5,000. Now remember, these all represent thousands. So as I go down through my table, I'm looking for a y value of 5. All right, so that would be 7 years. Now, we don't know what year they bought the car, so we would just say 7 years. All right, red-shouldered hawks were released into a region on January 2nd, 2023. The function f of x equals 220 times 1.05 to the x can be used to model the number of hawks in the region x years after 2023. Is the population increasing or decreasing, and explain? Well, the base of this exponent is 1.05, so that's above 1, which means this is a growth, so we would say increasing. And our reasoning for that is because b is greater than 1. How many hawks were released? And it means initially. This is our initial amount. So initially they released 220 hawks. In what year? In what year? That's x. Will the number of hawks reach 280? So let's use our calculator to assist us. We have 220 times 1.05 to the x. Go ahead and graph it. All right. Now, you're not going to see anything on your graph. We're really just worried about the table, and we're looking for a value of 280. So a y value of 280, that would be 5 years. But it didn't say how many years. It said in what year. Well, x is the years after 2023. So if I add 5 years to that, that gives me 2028. All right, a museum purchased a painting and a sculpture in the same year. Their values are changing exponentially as shown. Which value is increasing more quickly? Now, I have the equation for the sculpture's value, but I do not have an equation for the painting. So if you think about your equation here, I need to know what b is. And if I want to solve for b, I have to have an x, a y, and an a. Well, I know the a because its initial value here, years since I've owned this painting, I guess, it's at 40. So no years have passed and it's at 40, and that would be 1,000. So I know that A is 40. I'm trying to find B, but I need an X and a Y. So I can use this point as my X and my Y to solve for B. So I'm going to plug 64.4 in for Y, and I'm going to plug 5 in for X, and then I'm just going to solve. So I divide by 40. That gives me B to the 5th is equal to 64.4 divided by 40. And then I can get rid of this 5th power by doing a 5th root. And when I do that, I'm just going to round this. You get 1.1. So let's talk sculpture first. So for the sculpture, my number here is 1.075. So I am 0.075 above 1. If I move that 2 places, that would be a 7.5% growth rate. Now let's talk painting. I am 0.1 above 1. So if I move that 2 places, that would be 10%. So I have a 10% rate of growth. So the painting's value is increasing more quickly.